Hey y'all, today we are going to talk about buffers. So when we discussed equilibrium earlier, and we talked about Le Chatelier's principle, we talked about how we could change the concentrations of either a reactant or a product to cause a shift in the equilibrium towards a removal or away from an addition. So when we think about the equilibrium of, let's say, an acid. So here on the paper, we have the chemical equation for the equilibrium of acetic acid, which is a weak acid. We see if I increase the concentration of my acetic acid, I could cause a shift towards my products and create more H plus and more acetate ion. If, on the other side, I add in something into that mixture that has acetate ion in it, I could cause a shift back towards the reactants, reducing the amount of H plus I have in the solution. I also could add in more H plus to cause the same shift. If I add in H plus, I could cause a shift this direction. So because of this idea of these shifts and having different concentrations cause us to shift towards the reactants or the products, we can make a system of chemicals called a buffer. So in a buffer, we include two chemicals. We are going to include the weak acid or weak base, and we are going to include a salt or an ionic compound that contains the ion of the conjugate. So in this case, we would put in some acetic acid. We would also add in a salt that contains acetate. For example, something like sodium acetate, because we know all sodium compounds are soluble. By placing both the weak acid and its conjugate salt into the same mixture, we have some of this chemical in the mixture already. We have some of this chemical in the mixture already, which means that if we have small additions to either side of that reaction, we're not going to cause too much of a shift. We have enough concentration on either side to form a buffer. So the word buffer not only is talking about how long it takes your videos to load on your phone, but a buffer can also be sort of a pillow or a cushion or a space surrounding something before something else happens. So you can have, in this case, we're going to form a buffer between adding in some chemical before the pH starts to drastically change. So buffers are created, these buffer solutions or buffer systems are created to make a system that is going to resist changes in pH. I can add a little bit of strong acid or a little bit of strong base to this mixture, and the pH is going to stay about the same. Now, I could add a ton of strong acid or a ton of strong base, and eventually I will be able to overcome that buffer system and I will be able to drastically change the pH. If I overwhelm it so much that there's just so much extra H plus in that solution, it's still going to drastically shift. Or so much extra OH minus that it's going to drastically shift. That's possible. Buffers exist lots of places in the world in nature. Your blood has a carbonate buffer in it with carbonic acid and a carbonate salt so that your blood stays right around a pH of 7.4. That is just basic enough to try to prevent viruses and bacteria from living in your blood. There are enzyme buffers in order for enzymatic activity to happen. Those enzymes exist in buffer solutions that allow that to maintain the right pH for that enzymatic activity to happen. What else? Different companies put buffers into cleaning products, especially cleaning products that are going to come in contact with your skin. They might want to make sure that they can keep the pH at the right level for a shampoo, because we still need the cleaning detergent in the shampoo to be able to clean your hair, but we don't want the pH to be so high that it starts to damage your skin because you're having too much basic or alkaline substances on your skin that can really cause a lot of problems to your skin. So they might buffer that solution so that they reduce down the pH, but still have those detergents in the shampoo. So good buffer solutions are made from, like I said, a weak acid or base, and then something that has that conjugate ion in it. The best buffers have a consistent concentration between that weak acid or base and its conjugate. So the ratio of those concentrations is 1. That makes the best buffering capacity possible. In order to help us do the math and the calculations that this is going to require, we could do ice charts. We could totally do ice charts, but the math of the ice charts gets gross. It gets very complicated. It gets to the point where we cannot avoid quadratics or doing some sort of weird estimates to make things happen. The easiest way to do these calculations is with this equation called the Henderson-Hasselbalch equation. It is on your equation sheet, on your blue equation sheets. This version is the one that's on your equation sheet. So the pH of a buffer solution is equal to the pKa. Remember that pKa is the negative log of your Ka value, plus the log of the ratio of concentrations of that conjugate and the weak acid. We can convert over the Henderson-Hasselbalch equation to talk about bases instead, where the pOH is equal to the pKb, or the negative log of the Kb, plus the log of the conjugate over the concentration of the base. This equation is the manipulation of the data we would get from the ice chart. So we don't have to worry about doing all of the work in the ice chart. All we need to make sure is that we have good concentrations of our acid or base and its conjugate. In order to do this math, we need to think about what is in this buffer system, whether we're dealing with a weak acid or a weak base, and what its conjugate is. Sometimes we might have to do some math to be able to find the molarities, especially if we're talking about what volumes we're adding together. We might have to do some molarity calculations there. But in general, we are going to set these up very similarly to everything else that we've been doing. So for example, let's take a look at number 51. So we need to calculate the pH of a solution containing 0.75 molar lactic acid. Lactic acid is an acid that is formed in your body, especially in your muscles. When you get muscle aches, it's because your body is forming a lot of lactic acid, which tightens up your muscles. So we have 0.75 molar lactic acid. They give us the Ka for that lactic acid, and then 0.25 molar sodium lactate. So we can see how lactic acid and our sodium lactate have a common ion with each other. So if I write out the chemical equation for lactic acid dissociating, like we have been doing for all of our weak acids for the last couple sections, double-sided arrow, because I have weak acid, I'm in equilibrium. C3H5O2 plus H3O plus. I can see that here is that lactic acid. And here is the ion from the sodium lactate. Sodium lactate, because it has a sodium ion on there, we know that this is going to be soluble based on our solubility rules. All sodium substances are soluble. So this really exists as a sodium ion and that lactate ion. So that lactate ion is what's going on right here. So I know my concentration of lactic acid. I know my concentration of sodium lactate. So I know my concentration of lactate ion. By combining these two chemicals, I have created a buffer solution. By having some concentration on my reactant side of this equation and some concentration of my products, that sort of has balanced out that seesaw, right? It has created that buffer where I could shift a little bit towards the left or a little bit towards the right, and it's not going to drastically change the concentration of my H3O+. So I can use the Henderson-Hasselbalch equation. So pH equals pKa plus the log of A minus over HA. I can plug in my values, and I can find what pH this buffer solution would make. So the pKa is the negative log of my Ka. Come on, erase so I can read it. 1.4 times 10 to the negative 4 plus the log of the A minus concentration, that's that lactate ion, so 0.25 molar over the concentration of my acid, which is 0.75. Now looking at that ratio of concentrations, that is not super close to 1. That's a third. And so this would be an okay buffer, but it is not as good at buffering or maintaining this pH as it would be if those concentrations were equal to each other. So I plug this into my calculator. Make sure you're being very careful with your positive and negative signs. And I get a pH of 3.38, which means this buffer solution, this combination of lactic acid and sodium lactate, would like to maintain a pH around 3.38. That is the pH that it would like to maintain. I could add a small amount of strong acid to this, and it would drop the pH a little bit, but not much. And by a little bit, we're talking like tenths or less than a tenth of a pH. If I added a strong base to this, that strong base would increase the pH, but only slightly. Again, we're talking within tenths of a pH measurement. Down here a little bit farther on the page, it talks about a strong acid attack and a strong base attack. I highly recommend reading these and making sure that this makes sense. This sort of walks you through the process of why a buffer works and how it can handle that addition of lots of H plus or lots of OH minus and still maintain the same pH as it started with. When we make a buffer solution, the easiest way to determine whether a buffer is going to be good is to choose an acid or a base that has the pKa of that acid as close to the pH that we want to maintain as possible. So for example, when we're talking about the buffer in your circulatory system in your blood, we want to keep that pH really close to 7.4. So we need to find a buffer system that has a pKa that would also be very close to 7.4. Now, we can tweak that pH to be a little bit closer or a little bit farther away from what we need it to be by changing the concentrations of those weak acid and the salt that has its conjugate by using that Henderson-Hasselbalch equation to fine tune that pH to as close as we want it to be. when I want to give you just a quick heads up on example number 56. There is a question that asks how to calculate the pH after we have added some strong acid. Those calculation questions are really no longer involved in the AP exam. I left that one on there on purpose. So make sure to try to work that one out and check out the answer key, because we can see how close to pushing us over our buffer capacity a question is, by setting up an ice chart and seeing how that all works out. I'm not going to spend time in this video working it out because it's not something that you specifically need to be able to recreate on an AP exam question, but I think it is a good thing that might help you understand what's going on in buffer systems as you're working that out. Buffers is something that we are going to work on a lot in class. We're going to do a lot of problems together. We're actually probably going to do some of these practice problems together, so don't stress too much about getting them all done on your own. We also are going to do a lab where we actually create several buffer solutions and add strong acids and strong bases to those buffer solutions to see how far we can push them until the buffer is broken before we exceed its capacity. If you have any questions, make sure you let me know. Like I said, we're going to work through this slowly and steadily, and I will see y'all later. Bye.